So third segment for chapter 5. So we just finished up looking at the ion-electron method in acidic solution. So we would add, first we would balance our each half by non-hydrogen, non-oxygen elements. Then we would balance our oxygens. Then we would add water to balance the oxygens. Then add H pluses to balance the waters. And next what we're going to look at is what happens if it's a basic solution. All right, it's a basic solution. So obviously we can't have any H plus left over because that's an acidic solution. So we need to make sure it's a basic solution by neutralizing those H pluses. The simplest way to balance the equation in a basic solution is to use those first 7 steps that we just looked at in segment 2. Then once you get to that point, so you've got it balanced in an acidic solution, the next thing you're going to do is add the same number of hydroxides to both sides of the equation as there is H plus. Obviously then the H plus and the OH minus will form water. And of course, just like algebra, whatever we do to one side, we do to the other. So if we add 8 hydroxides to one side, we're going to add 8 hydroxides to the other. The one side will turn all of the H plus into water, and now we have a basic solution. We'll cancel out any waters that we formed that may have been on the other side of the equation. So if we look at our previous reaction, where we were looking at the dichromate and the Fe2 plus, right? When we added to both sides of the equation the same number of hydroxide as there are H plus, and if you recall, here's the reaction. We had 6 Fe2 plus 14 H plus the dichromate goes to 6 Fe3 plus 2 chromium 3 pluses and 7 waters. Now what we're going to do is we're going to balance out the H plus by adding 14 hydroxides to both sides. Okay, that means the 14H plus the 14OH minus will form waters. So now we have 14 waters on the reactant side and 14 OH minuses on the product side. And now that last step will be to cancel out the waters. We have 14 waters on the reactant side, 7 waters on the product side. We'll cancel those out and change that to 7 so that our final reaction is now 6 Fe2 plus 7 waters plus the dichromate will give us 6 Fe3 pluses plus 2 chromium 3 pluses plus 14 hydroxides. And now we have a basic solution because we have OH minus instead of H plus. So that's how easy it can be. But again, it's 10 steps. The first 7 would be the same no matter what your solution is, whether it's acidic or basic. All right, which of the following is a correctly balanced reduction half reaction? So a reduction half reaction. So here we have Fe3 plus the electron goes to Fe. And of course that's not balanced, right, because the charges are not correct. Then we have 2Fe going to 2Fe3 plus. That's oxidation, that's not reduction. Then we have manganese 2 plus going to manganese 7 plus. That's oxidation, that's not reduction. Then we have 2O2 minus going to O2. So we are going -2 to 0. That's oxidation again, not reduction. And then finally we have Mg2 plus the 2 electrons going to Mg, and now we can see everything's balanced, and that is our correct answer. All right, balance the following reaction in acidic solution. Now, this is going to take a while, I'm sure, right? But there are your options. Make sure you go ahead and just, pause it here, write everything out because it's going to take you a bit probably. And then hopefully you'll start playing again, and somewhere right about now maybe you figured out the answer is C. All right. Let's see. Doesn't appear that they're going to help us with that one at all. So maybe we should go through this. So we're going to have iodine going to I2. So iodide going to I2. We have the HNO2 going to NO. So those are going to be our 2 half reactions. So this guy is going here. This guy's going there. And I'm going to go ahead and get rid of all of our answers here. So we have some space to work. All right, so we're going to look at I minus going to I2. So we are going to need a 2 on this side, right? Because we're going to need 2 iodines here. We have I2 over there. So now my non-oxygen, non-hydrogen, they're balanced. Now I want to balance oxygen. Don't need to add anything. Then balance hydrogen. Don't need to add anything. Then it'll be charge. So we have 2 minus 1s over here, which means we're going to add 2 electrons over there. Now we're going to look at the other half. We have H NO2 going to NO. So we don't worry about hydrogen or oxygen. We have 1 nitrogen, 1 nitrogen. Next we'll balance oxygens. We have 2 on the reactant side, but only 1 on the product side. So we're going to add 1 water to balance the oxygen. Oxygens are now balanced. Then we're going to balance our hydrogens. We have 1 hydrogen on this side and 2 hydrogens over here. So we're going to add 1 H plus over here. All right, now we're going to do our charge balance. We have +1, neutral, neutral, neutral. So we're going to add 1 electron to this side. Now to make our charge balances out, we have 1 electron on this side, 2 electrons over there. So we're going to multiply this whole thing by 2. My 2 electrons will now cancel out. And now I'm ready to write out the whole reaction. So we have 2 times the H plus 2 times the HNO2 plus 2 iodide goes to 2 NO plus 2 H2O plus the iodine, I2. All right. So if we did everything correct, according to the slide, our answer was 2H plus, good, 2HNO2, good, 2 iodide, good, 2 NO, good, 1 I2, good, 2 waters, good. All right, hopefully that all made sense then. You might have to watch that a couple more times, or maybe you got it right the first time on your own. Let's hope. If you're struggling with any of this, I'm going to go ahead and post another instructor who goes through this. He does a wonderful job with it, and I'll put that under practice sets, where he simply just goes through balancing acidic solution oxidation reduction equations. And that's Tyler DeWitt. You can even follow him. He does a great job of doing a lot of these processes as we're going through the textbook. I've referred to him quite a bit in previous semesters because he does a wonderful job with these videos. All right, so moving right along then, we have ion-electron method balance the following equation in basic solution. All right, so in basic solution. So we're going to take MnO4 minus plus HSO3 minus. It's going to go to Mn2 plus SO42 minus. So a lot of these species will look kind of crazy and they can sometimes be overwhelming. So what you're going to do is just relax. Remember, you're going to break it into its 2 half reactions. A lot of times to do that, what I'm looking for are common elements. Remember, we're going to be adding oxygen and hydrogen. So typically I try to focus on things that are not oxygen or hydrogen. So like manganese, I know has to go to manganese, right? And sulfur, I know has to go to sulfur. And the oxygen and the hydrogen, I'll figure that all out later as I go, right? So that helps to break it down, make it a little more simple, take away some of that overwhelming feeling from it. So in our first half, we're going to have MnO4 minus going to Mn2 plus. And in that second half, we'll have that HSO3 minus going to the SO42 minus. And now, of course, we're just going to balance the atoms other than the hydrogen and the oxygen, right? So we'll start with that MnO4 and the Mn2 plus. We have 4 oxygens on the reactant side, but we have no oxygen on the product side. The manganese themselves are balanced. We have the HSO3 and the SO4 here. The S's are balanced. Don't have to do anything there. I started jumping ahead. I was adding those waters already, trying to get this bad boy done. So there it is. We'll add our 4 waters to make up for those 4 oxygens. For the SO3 going to SO4, we have 1 extra oxygen, so we'll throw 1 water on the reactant side. All right, so now our oxygens are balanced, our non-hydrogen oxygens are balanced. It's just a matter of the hydrogens left over. So we'll add H plus in order to balance the H's. And so for the MnO4 going to Mn, we know we added 4 waters. That's going to give us 8 hydrogens, so we're going to add 8 H plus. For the SO3, we added 1 water, and so over here we're going to add 3 H plus. Now, why 3? Don't forget, we had a hydrogen already over here, right? So we took the 2 from the water we added, plus 1 from the HSO3. All right, now we're going to balance the net charge to get our electrons, right? And so here we're going to take that 8H plus minus 1. That's going to give us a total of plus 7. And then we're going to take plus 2 plus neutral is plus 2. So that means I need to add 5 electrons to the reactant side to give me a plus 2 on both sides. For the H2O plus the HSO3 minus, remember we added 3 pluses to the product side here, so we have a negative 1 on the reactant side and a plus 1 on the product side. So we're going to add 2 electrons to our product side here. All right, now we want to make the electrons the same for the loss and the gain. So here's our 2 half reactions. And in order to make this work, we're going to multiply the first equation by 2, right? Because I need to get 5 electrons and 2 electrons to balance out. So I'm just going to switch them around, multiply the 5 by 2 and multiply the 2 by 5, right? So again, we have to multiply in order to get the half reactions to balance. Now we have 10 electrons on each side, which means the electrons will cancel out. So we have 10 electrons plus 16H plus 2 MnO4, and then we also have 5 waters and 5 HSO3s. And on the product sides, we're going to have 2 Mn, 2 pluses, 8 waters, 5 sulfates, 15 H pluses, and 10 electrons. So, summing everything up, there it is. We'll make the 10 electrons go away from each side. And now we can start canceling some of the other stuff out, right? We have 5 waters on the reactant side, 8 waters on the product side, which means we can cancel some of those out, turn that into a 3 on the product side. We have 16 H pluses on the reactant side, 15 on the product side. We'll cancel those out so we only have 1 on the reactant side. So there it is. We canceled everything that was the same. Now we're going to pull those out of the equation and rewrite it. And so we have H plus 2 MnO4 minus plus 5 HSO3s produces 2 Mn, 2 pluses, plus 3 waters, plus 5 SO4, 2 minuses. Again, that's balanced in acid, right? So we did everything the same, but remember, we wanted to do this in base. So to balance it in base, now what we're going to do is add those hydroxides. So since we have H plus on the reactant side, we're going to add 1 hydroxide to each side. We'll combine those hydroxides with the acid to form water. All right, so there's my water. And so now we have 1 water, and of course we have a hydroxide on the product side. Now we can cancel that water out with the 3 waters on the product side. And so now we'll rewrite it to be 2 MnO4 minus plus 5 HSO3 gives us the 2 Mn, 2 plus 2 waters instead of 3, plus the hydroxide, because now we're in a basic solution, plus 5 SO4, 2 minus. All right. So balance each equation in the solution indicated by the skeletal reaction using the ion-electron method. So we're going to take the manganate, permanganate plus oxalate goes to MnO2 plus CO3 2 minus plus H plus in acid. All right, so you want to pause here. Go ahead and work this out. Hopefully your final answer will be 2MnO4 minus plus 3C2O4 2 minus plus 2 waters goes to 2MnO2 plus 4H plus 6CO3 2 minus. Second one I want you to do is ClO minus plus VO3 minus. It's going to go to ClO3 minus plus the vanadium 3 hydroxide plus OH minus, and this time in base. And of course, your final answer will look like that. Now, if you struggle with these, make sure you get in contact with me. But remember, you're going to follow the 7 steps like you're in acid for both of them. So the first thing we do is break them into their half reactions. Then you're going to balance the oxygen, balance the non-oxygen, non-hydrogens. Then you're going to balance the oxygen. Then you're going to balance the hydrogen. Then for the basic ones, you'll then cancel out the hydrogens to make it a base. Okay. So again, if you struggle with those, make sure you get in touch with me and we'll work through it, see how it goes. All right, so acids as oxidizing agents. So the fun stuff of this is taking a metal and we react it with an acid. We actually had the opportunity to do that just recently. We took a piece of magnesium and we reacted it with HCl, right? Now, in that solution, then we formed metal ions and, of course, hydrogen gas. So if we had taken a light or a match, put that over top of the test tube, we would have gotten a nice little poop noise, which would have been the hydrogen gas burning, right? Now, the molecular equation, for instance, would be zinc plus 2HCl goes to H2 plus ZnCl2. Now, we've already learned how to write it as a net ionic equation, right? So we would have zinc solid plus H plus goes to H2 gas plus Zn2 plus, where here we know the chlorine becomes a chloride and is a spectator ion. We can now say that the zinc we know has now been oxidized because it went from 0 to +2. We know the hydrogen has been reduced because it went from +1 to 0. Okay? We know that the hydrogen then would be the oxidizing agent, and we know that the zinc would be the reducing agent. So that's all the different things we've looked at and all the different ways to look at it, even though we've been looking at the same thing. All right, so for the ease of the oxidation process, it will depend on the metal. All right, so the ease of oxidation process is going to depend on the metal. So basically the metal is going to react with either HCl or H2SO4, right? So the metal then is easily oxidized by the H+. The more active the hydrogen is, the more likely this is to happen. So magnesium, zinc, alkali metals will all react with acid. So we'll have magnesium plus 2H plus goes to Mg2 plus H2. And that's the reaction we actually witnessed in lab. We have 2 sodium plus 2H plus goes to 2 sodium plus H2 gas. You can see it's repetitive here. The metal is going to react with the H plus. It's going to produce hydrogen gas and give us the metal ion. Now, metals that don't react with these two means they're not going to be oxidized by H+, means they're less active than the hydrogen gas. And so what we're going to do here is build what's called the activity series, okay? And again, you can sort of front load this if you want by pulling that activity series down, and you'll see usually somewhere in the middle of the chart, it'll say something like acid. And then there'll be metals that are underneath of it, and there'll be metals that are above it. Okay, the metals that are above it are the ones that were more active than the H+, so more active than H gas, right? So hydrogen gas. And the ones that are below it are the ones that are going to be less active. So like copper and platinum, right? So a lot of the jewelry we wear, typically those are metals that are less active than hydrogen. So they don't react with the acids at all. Now the anion determines the oxidizing power. So acids are divided into 2 classes: non-oxidizing acids, which means we have the anion as a weaker oxidizing agent than H3O plus, the hydronium. Only redox reaction then is going to be 2H plus going to the gas, or the hydronium going to hydrogen gas in the water. HCl, HBr, and HI. Okay, so non-oxidizing acids. H3PO4 if it's cold and dilute sulfuric acid, and most organic acids. The second class would be oxidizing acids. Here the anion is stronger than the oxidizing agent, so used to react with metals that are less active than H+, or H2, excuse me. There'll be no hydrogen gas formed, so like HNO3, if it's concentrated or dilute, it can be very dilute with a strong reducing agent. We could have H2SO4. If it's hot, concentrated with strong reducing agent. We could also look at nitrate ion as an oxidizing agent. So basically we're going through just the different acids here and looking at how they can react. Okay, so concentrated HNO3. Here the nitrate will be more powerful oxidizing agent than the H+. So the NO2 would be the product, right? So we'll make nitrogen dioxide gas as a product. The partial reduction of nitrogen will go from +5 to +4. So we have nitrate plus the acid plus an electron would give us nitrogen dioxide gas and water. So in other words, we could take copper, we could mix it with nitrate under acidic conditions. So we added acidic nitric acid. The copper now will oxidize to the Cu2+ as the nitrate becomes NO2 gas. So in other words, we took copper, we mix it with something like HCl or H2SO4, nothing happens. But if we add it with nitric acid, now something will happen. All right, so dilute HNO3, the NO3- is more powerful than the H+. Now NO is going to be the product, so we get a partial reduction now of nitrogen going from 5 to 2. So nitrate plus 3 electrons now gives us the NO gas and 2 waters. Now here we can use these to react with metals that are less reactive than the H2 as well. So again, reaction of copper with dilute nitric acid. We take 3 coppers, 8 nitric acids, gives us 3 copper nitrates, 2 NO gases, and 4 waters. Now, you don't have to memorize all of these. This is just what's going on. And so when you see these reactions, you know, so it would, I guess, rewind it a little bit. The reason why we used to worry about this is we used to do the synthetic process of copper. So we would start with copper metal, and we would take it through a series of reactions and bring it back around to copper. And so a lot of those reactions get shown here by this activity series. Okay. So again, we're going to kind of go fast through some of these because again, you don't need to memorize these. It's just looking at the different acids and how they react with the metals. All right. So which of the following statements about oxidizing acids is false? So H2SO4 can behave as either an oxidizing or a non-oxidizing acid depending on the solution conditions. Is that false? No, that was true. Go back and look through the slides. Oxidizing acids can oxidize metals that are less active than hydrogen. Yeah, that's true. The anions of oxidizing acids are reduced in their reactions with metals. Yeah, that's true. Most strong acids are oxidizing acids. Well, that wasn't true at all, right? We broke it all down. Nitric acid's a strong acid. Sulfuric acid was a strong acid. So that must be the one that's false, right? And oxidizing acids are acids whose anions are stronger. That's definitely true. All right, so the redox reactions of metals then. Acids reacting with metal. Special case of more general phenomena. So of course we've seen this as the single replacement reaction. This is the reaction where one element replaces another, right? So that general formula was A plus BC goes to AC plus B. So metal A can replace metal B. Now, back in Chem 110 or maybe in high school, you may not have had to worry about whether or not the reaction would or would not react. I know for my classes, when I teach 110, I pretty much tell them everything that Mr. Caro gives you works. And that's simply because they don't have to have responsibilities about the activity series. But here in 150, you do. And so we've already seen solubility can affect reactivity to where if we make something that's insoluble versus if we make something that's not. So in other words, if both products are soluble, we saw that that was a no reaction. So it had to either form a precipitate, it had to form a gas, or it had to form molecular water, or it didn't work, right? And here we're going to see that it depends on the metals. If A is more active metal, or the nonmetal A can replace nonmetal C if A is more active than C, right? So again, A could be either a metal or a nonmetal. The metals always replace the metals, and nonmetals always replace nonmetals. But now it comes down to a reactivity series. Which metal is more reactive? So if I have a metal replacing a metal, so let's say we have sodium reacting with copper chloride, is sodium more active than copper? Because if it is, then it's going to replace the copper. If it's not, then it cannot replace the copper, right? And so again, this is going to lead us to our activity series. So it's a single replacement reaction. Here on the left, we have zinc solid and copper sulfate solution. And again, this is something you would have been able to observe in a normal semester. So, we would have had a lab where you would have actually taken some zinc, and we do not use a zinc strip though. We use zinc turnings, so like chunks of zinc, and we put that into copper solution. And basically we see what happens is in the center here, you can see that zinc strip is starting to turn brown. And you can see the solution is just a little less blue, right? Just a little less. And then of course, when we get all the way to the right, we see now we have this reddish stuff going on top of the zinc. That's actually copper. And now when we look at our blue solution, it's even less blue. And then really some of the fine detail, of course here you can see a little bit of chunks in there, but I wish that one was clear and they would show more of the stuff going on here, because if you take that strip and you bang it across the beaker here, you see a lot of that stuff fall off. That copper would fall off and has like a black tinge to it when it's in that blue solution. If we leave enough zinc in there, eventually that blue solution becomes completely clear, right? And so that was one of the things we would do in lab. And of course, that's representing this reaction. We have zinc solid plus, in this case, copper sulfate. The copper sulfate is going to break down. The zinc is going to become zinc sulfate. Now it's ionic, so it's not the salt yet, and copper metal. But of course, you could take this another step further, right? If we took that copper and we filtered it out and then boiled the water down, we would have zinc sulfate as a salt in the bottom of that beaker. All right, so your single replacement reaction then, Zn2 plus ions are taking the place of the copper 2 plus ions in solution. Copper atoms are taking place of the zinc atoms in solid. So Cu2 plus oxidizes the zinc to zinc 2. And the zinc, of course, reduces the copper to copper 0. The more active zinc replaces the less active copper. Okay, so zinc is easier to oxidize. And again, we could actually predict this based upon the activity series of metals. So Cu we know is going to be less active and can't replace the zinc. So if we're looking at our series then, typically we'll have zinc above copper. So the things that are above can replace anything that's below it, but it can't replace anything above it. Okay, so we can't reduce the Zn2 plus, which means copper solid plus Zn2 plus would lead to no reaction. Right? So it's a general phenomenon. A metal that is more easily oxidized will displace one that is less easily oxidized from its compounds. And again, this is the activity series. Metals at the bottom are more easily oxidized, more active than those at the top. So here, it's pretty small writing here. We have gold at the top here, and then of course rubidium at the bottom here. Some charts, and the one I'm referencing, typically this is switched around, so we would have the more active at the top. But the way this one's written is things up here cannot replace the ones that are down here. So zinc is here, and then we would find, we mix that with copper. Copper is here. So like I said, this picture from your textbook is backwards to one of usually the ones I use, the ones that are in the, on the period, not the periodic table, excuse me, on Google. The Google images I bring up, a lot of the activity series, usually this is going to be flipped around, so zinc would be on top. But here, whatever's on top cannot replace what's underneath of it, but anything that's underneath of it can replace it. So if I take copper solution and mix it with a lead solution, the lead would replace the copper, right? Hopefully that kind of makes sense. Now, how the activity series is generated, We're already at about 30 minutes here, way over where I want to be. So I think we can stop here and we'll pick up with the next segment, looking at how the activity series can be generated and what we can do with it and how we would use it. All right, so stay tuned for the fourth segment.